We are group 9. This is our final report. We are Sebastian, Anastasios, Amy, and Elizabeth. We are going to talk about all the analysis we do on the program and how we paralyze the paralyzed things we can do. First, to analyze the program, we create the call graph where we can see the different programs that are dependent from the others. Like for example, in the puzzle div, the main program calls different classes, and each of them make different functions. For example, in the vectors is the part of the program that make all the calculations about the distance between the image and the length that they have. Like they use the vector collision length with this in the algorithm. Also, he calls to the puzzle Z to see where there is any error or something that have in the image or in the analysis. And also puzzle div calls to CVC and DVC, that are the classes where the image are processed before going to the vector part. In the class there have a lot of different methods. For example, one puzzle D calls all the methods of puzzle of tunables, where it goes to the set constant barrier and cropping ratio. And in this class, in tunables, they have a lot of dependency between the data that are sent, so it cannot be able to make any parallelization in this part. And also in the main calls to, when it calls to CVC, CVC is the one that calls to DVC, so they are like, if one is working, the other have to work as well. And they call to the DVC to the different methods they have to initialize a value, and to if they have an error, they call to show the error that a file have.
About the analysis of the given sequential code, we made some changes that we can compare a specific image with a whole folder, and then we run some tests, so we tune and we take some results about the time we need. That was the first run, and here's the second, and here we have the methods, functions, hotspots, and here we have the functions that they spend more time in the CPU, and we try to parallelize these functions to make the program run in less time.
We parallelize in the program the method of vector ops, DVC and CVC, and in the main program, we parallelize this part where is to see the files and compare one image with all the files of that directory. In vector ops, we parallelize the part of the Euclidean distance, and we do this like changing the force to a whiles. And in the DVC, we use like reducer to make the sum and to don't lose like data. This is a part of seals. We change the while, like we can see here, we change the while for a for with the same conditions, so we could be able to parallelize. In DVC, we parallelize in almost all the methods, and in CVC is the same. We can see here that we parallelize in the class of making the for more quickly when it's like a puzzle will be cut off now.
Okay, our strategy was at the beginning we parallelized everything that was possible to parallelize without any race condition or any trouble. and after we thought that we would find the parts that are better not to parallelize, but we found that it's better to parallelize everything that can be parallelized. And well, in the main program we had some troubles with, well, we used mutets that, and we used the implementation that there's in the documentation, in the silk documentation, but it didn't work. So we changed the implementation that well, we have 500 spots, and we use the heap after computing the 500 pictures parallelly. For the results of the lab in the Shannon machine was like in the medium set of image in the SSD, it was like a little more than 3 minutes. We tested twice and it didn't change it almost. In the spinning disk, it was like a little less than 4 minutes. In the large set of image, it was about 20 minutes and a half, and in the spinning disk, it was a little less than twice in the SSD. It was about 35 minutes. So yeah, that was the results of the tests. And the very large image set didn't work, but we think that it's a library problem, and